Alright, so we'll go over set theory. Okay, so what basically is set theory? So set theory, we have to basically define what a set is. So a set is a collection of well-defined objects. So if you're going to have numbers, let's say numbers less than 10, this is an example of a basic set. Okay, so a set is a collection of well-defined objects. So we're going to call the objects to be members. We can call them elements. So members or elements are contained in a set. So in this case, you can say 1 is a member of that set. You can also say 1 is an element of that set. Okay, so if we said A is the name of a set, we are going to see that we can actually say that A, if you're going to get any element, for example 1, you can say 1 is a member of set A. So we're going to talk more about these as we talk about the notation. But now we've talked about the basic introduction of it. We know what a set is. So we can express a set in what we call, this is called roster form when you see this kind of brackets, the curly brackets. Okay? So under the study of set theory, we're going to look at the different kinds of sets. We're going to look at the sets on the number line where you basically use an interval. Instead of using these brackets, you can use, for example, these brackets 1 to 4. You can use 1 to 4 like that. You can also combine the different kind of brackets like that. So all these are going to be explained later on in this topic. Okay, so don't worry, you basically get to understand what that denotes. Now let's try to break down the set theory notation, beginning with what you already know. Okay, so let me first of all classify the sets according to numbers. So let's talk about the sets of numbers before we proceed and look at the notation. So what are sets of numbers? So we can classify numbers in different categories. Okay, so I'll give you a list of different kinds of numbers we can have, and then give you a chance to try to classify them before I give them names. So we have numbers 1, 2, 3, 4. So these are counting numbers beginning from 1. And then we have numbers that can also be counting, except we include a 0. Okay? Then another set that you can think of is, so let me first of all classify these ones that we have already. The first one is called a set of natural numbers, and then the other set is called a set of all numbers. Okay, so we can proceed actually and move and have other kinds of numbers. So we have what we call integers. So integers include the negative numbers. So you can have negative 1, 0, 1, and 2. Of course, not ending on either sides. So these are called integers. Okay, so integers are represented using a letter Z. Then the other sets of numbers we can look at are what we call rational numbers. So rational numbers are numbers that can be expressed in the form of A over B. So all integers, all the numbers we've talked about so far are rational, in that they can be expressed in the form of A over B. So these numbers would include, in addition to the integers, it's going to include the numbers like fractions, 1 over 2, that's a 1 over 2. So any number that you're able to express in the form of a fraction, A over B, and of course, including the integers, they can also be expressed in this form. Now, except B can never be equal to 0. So another rational number that may interest you is what we call the recurring decimals, right? So if you've come across numbers like 0.3 recurring, it implies 0.333 without ending. Okay, so all these are rational numbers for your own information, because there are questions that can ask us to like convert these recurring decimals to a fraction. Whether it's of different numbers at the end, it may be like this, which of course means 0.3 and then 141414 recurring, right? so it can still be expressed in form of a fraction. Now, the other set of possible sets of numbers are what we call irrational numbers. So irrational numbers are numbers that we cannot express in the form of a over b, and these involve these imperfect squares, square roots, right? So root of 2, root of 3, root of 5, and other numbers that you can't find the perfect square, they are all irrational numbers. But they are not the only ones. There are some decimal numbers, numbers like a pi, that you can't express in the form of a over b. So all those are irrational numbers. Okay. Now there's a bigger set which combines all the rational and the irrational numbers. Okay, which is a set we call real numbers. Very common set of numbers. So real numbers is a set of all numbers. I actually like calling them numbers that make sense. Okay, numbers that exist, numbers that are not imaginary, they are called real numbers. So all the rational and irrational combined together give us what we are calling the set of real numbers. So you notice that the set of real numbers consists of all the numbers we've talked about so far: the integers, the odd numbers, the natural numbers. They are all part of real numbers. Now, is this the biggest set of numbers that we have? No. There's what we call complex numbers. So complex numbers is the biggest set of numbers. All real numbers are complex numbers. So real numbers is a subset of complex numbers. Now, what makes complex numbers different or a bigger set is that it involves the imaginary numbers, the I squared. So numbers that you're able to express in the form of a plus ib are all complex numbers. So we've talked about the different sets of numbers, and then also their subsets. Okay, now we can break this down actually and go further and classify these numbers into other sets. We can talk about what we call even numbers, we have what we call odd numbers, we have what we call prime numbers. What else do we have? So we have, I can also say we have what we call factors, right? And then we also have what we call multiples. Okay, of course the last two are not sets, I'm just trying to explain them. So what are even numbers? Even numbers are numbers that if you divide by 2 gives a remainder of a 0. So 0 itself is an even number. So 0, 2, 4, 6, 8, and so on and so forth. Odd numbers, numbers that you can divide by. If you divide by 2 gives you a remainder of a 1. Okay? If you divide by 2 gives you a remainder of a 1. So I think we'll start from 1 itself. 1, 3, 5, 7, 9, 11. All these are odd numbers. Now, what are prime numbers? Now, prime numbers are a bit interesting. We call them numbers that you can divide by 1 and itself. 1 and itself. So you find that it's a bit interesting. So we're going to have 1, 3, 5, 7, 11. Now you see that 9 is not a prime number. Now, in fact, it doesn't start from 1. I've messed up there. Prime number is a number that divisible, numbers greater than 1 and divisible by 1 and itself. So 2 is a prime number. So 2, 3, 5, 7, 11. Why are we skipping 9? 9 is not only divisible by 1 and itself because 3 is also a factor. So 11, 13, 15 is not. So 17. So that's a set of prime numbers. Okay? And then factors. Factors, of course, are numbers that you can divide into. So if you say factors of 9, for example, factors of 9 would be 1, 3, 9, right? Itself. And then multiples. If you say the multiples of 9, or let me say multiples of 3, you begin thinking of what numbers I've got 3 as a factor. So 3 itself, 6, 9, 12. So those are the multiples of 3. So I thought this is very important for you to understand as we proceed under a study of set theory, because these are going to be very handy as we proceed. They are going to be used, especially as we begin looking at what we call the set builder notation. Okay, there may be cases where we may describe the set in roster form. X is such that X is a member of, not necessarily a member, let me say X is maybe less than 20, and then X is a member of let's say even numbers or real numbers. So that's why you need to know these symbols, what they stand for. So if I ask you to list such a set, you need to understand, okay, so if we're dealing with X is less than 20 and then X should be a member of real numbers, what does that mean? So what are real numbers? So obviously you know that this is going to be a very big set. You know that real numbers start from negative of infinity to its positive. So we are restricted to go only up to 20, right? So what it means, the set will be from negative infinity all the way up to 20, but 20 is not included. So that would be the interval. Now, trying to break it down to something that is simpler to you, if we say it's a member of natural numbers, it means we're going to list numbers from, natural numbers start from 1, right? 1, 2, all the way up to 19. These are the natural numbers that would qualify to be part of such a set. So I'm going to add some interesting questions that I've already solved under this concept called set builder notation, and I think it's going to be very helpful to help you understand more. Now let's proceed and review some of the notations that we have under set theory. So you're already conversant with the union, the intersection, the universal. You are also conversant with what else are you conversant with? I expect you're conversant with a complement. If we can say a complement, I believe you understand what it means. So I'm just going to explain this again. So a union of a set implies you combine all the elements together. The intersection means you go for the common elements. The universal is all the elements under study. The complement means outside or not contained in a given set, but within the universal set. So what does this mean? What does this mean? Let's look at a practical example. So we can declare our universal set. In this case, we can either use a capital letter E or U. They can still both denote the universal set. So if we are starting the numbers between 0 and let's say all the way up to 10, right? That becomes our universal set. There's going to be cases where the universal set can be declared to be a set of all real numbers. So that's why it was important and necessary for us to look at the sets of numbers before proceeding. Okay, so let's try to limit it to 0 to 10. So they can give you A to be a set of even numbers. Okay, even numbers. They can give you B to be a set of prime numbers. So you see why it's important for you to know these numbers, right? So before you can actually proceed to determining, let's say, questions like the intersection of A and B, the union, the complement of A intersection B, the complement of A. Okay, so you should be able to list what we have. So let me just move these questions a bit up and then see how we can handle it. Okay, so we'll start by listing A. So set A is containing even numbers. So even numbers are numbers divisible by 2 and give the remainder of a 0. So 0 itself is an even number, 2, 4, 6, 8, and 10 itself. For B, which is containing the prime numbers, numbers that are greater than 1 and divisible by 1 and itself, 2 is a prime number, 3, 5, 7, what else? 7, 12, 8, no, 9, no, 10, no. So 7 is the biggest prime number. So if you are going to be asked to find the intersection, what are the common elements between the two sets? I can see 2 is the only common element. 2 is the only even number, which is a prime number. A union B means you combine these elements together. So what would it mean? We're going to have 0, 2, 3, 4, 5, 6, 7, 8, 10. And then A intersection B complement, on the other hand, would imply you remove 2 from the universal set. What's a complement of A intersection B? It means the universal set without A intersection B. So if you're going to remove 2 from the universal set, whatever remains is going to be A intersection B complement. For A complement, it implies remove these elements again from the universal. What remains in the universal are going to be the complement of A. It means they are within the universal and outside A. So what are those numbers? So 1, 3, 5, 7, and 9. So I've introduced you to a set notation, and of course I did mention that we can have things like a member of a set, right? So if you're going to say set A is having members 1, 2, 3, you can say 2 is a member of set A. You can say 4 is not, so you cross. 4 is not a member of set A, as we can see, it's not there. Then there are things like the subsets. You can say, of course we're going to talk about subsets, but this is a subset of, okay, these are the two ones we're going to be dealing with. So this generally means a subset, and this means a proper subset. Okay, this is generally a subset, that other means it's a proper subset. Of course we're going to understand what a proper subset is and what just a subset is by definition, and of course by what we're going to look at. Now, a Venn diagram is not something that is new to you. We basically use a Venn diagram to represent details about a set. So in the previous example where I gave you an inverse set, so usually we use this for what we call the finite set. So they are going to be what we call an infinite set. Why am I saying a finite set? A finite set is a set that you're able to count the elements. There are going to be sets that are called infinite that you can't count. Sets like a set of real numbers, that's an infinite set. You can't express it in terms of a Venn diagram. You can't list it all. Now, finite sets are sets like where the universal set is limited. Let's say 0 to 10. You know that these numbers you're able to count them. Okay, so that's a case where we can use a Venn diagram. So the inverse set, the box itself represents the inverse set, meaning that all the elements that are going to be under study will be within the box. Now you can break it more into detail. You can name the inner sets A, B, and C. So what you're going to put there, usually these are the elements that are common in all the three sets, because we can see it as a point of intersection for all the three sets we have. At this point, you can put only elements common between A and B, only elements common between A and C, only elements common between B and C, and then the middle part, of course, all the elements common. Now, you've seen that I've focused more on the elementary form, where we can have set A to have 1, 2, 3, 4. If you are going to have set B containing 2, 4, 7, 8, and then you're going to have set C containing 1, 4, 8, 9. So What this would mean is, if you try to identify the common elements in all the three sets, we can see only 4 is common. 4 is common in all the three sets. So 4 would be the element there. Now you have to put a dot to indicate that 4 is an element. And then if you can look at B and C, I can see 8 is a common element. So a dot and then 8. If you can look at A and C, I can see 1 is common. And then if you can look at A and B, I can see 2 is common. So if I can go into A, what's remaining there? If I move 2 and 4, 1 and 3. So I'm putting a dot to indicate that they are members. For B, of course, you see that we have 7 remaining. For C, you have 9 remaining. So this is basically how you can go about this. So I've actually made a mistake. 1 is already included there. So let's say I added a 0 to that set. It would mean 0 would be. The idea here, I'm trying to show you that you can put more than a single element in a given set. So all the other elements that are within the universal set that are not inside can be outside. So you can see we have 0, 1. So 3 is not. No, 3 is there as well. 4 is there. 5 is not. 6 is not. 7 is not. 8 is. 9 is. So those ones are outside the 3 sets A, B, and C, but within the universal set. So you can indicate them using the Venn diagram in such a way. Now, the other kind of a Venn diagram that we can have is a Venn diagram that deals with numbers. Okay? These may be cases where, for example, you are dealing with focusing on a study of a class. Let's say you are trying to focus on a class of students with options. You may have people who are taking math as a compulsory subject, and then others may be taking civic education, and then others may be taking history. So in this case, you can't say 1, 2, what? No, you can just say, okay, how many students are taking math? 20. How many students are taking civic education? 30. How many students are taking history? 30. How many students are taking both math and civic education? 15. How many students are taking civic education and history? You can say 4, or let's say 10. How many students are taking both math and history? You can say 17. So the basic idea in a question that is set up like this is, in this case, when it comes to a Venn diagram, since you're dealing with how many, you're just going to be putting a single number. If you say 20, it means the 20 students are taking math. Okay? So I'm just trying to give you a picture. In such a case, you don't put a dot, because 20 is not a member, but 20 is a number of math students. But in practice, that's not basically what you do in terms of writing the 20. You don't just write the 20 directly as it is. You have to go for the students who are studying over 3. You start from the center and then until you reach the ends. But I was just trying to give you a picture on how I use a Venn diagram. And I'm going to add a video, a tutorial that's going to explain to you on how you can enter the information in a Venn diagram in an orderly manner. Okay, I just thought I needed to mention as we introduce it. And then we now have what we call power sets. What is a power set? So a power set, of course, makes more sense after you talk about subsets. So let me start with the subsets and then we get back to the power sets. So what is a subset? So a subset is a set contained in another set. Contained in another set. That's what a subset is. So if you're going to say, I'm going to start with the smallest set we can have, consisting of members 1 and 2. So what are the possible sets we can come up with that are contained in A? So an empty set is also a subset. 1 is a subset, and then 2 is a subset. So these sets that I've written there are contained in A. Now, the set itself is also contained in itself. So you notice that in addition to the empty set, the set itself is also a subset, including the cases where you can have minimal elements as well. So you can see that a set containing two members has got 4 subsets. What if we said we had set B containing 0, 1, and 2? What are the possible subsets? So an empty set itself is a subset containing 0, containing 1, containing 2. You can also have a case where you could begin combining. You can have 0 and 1. You can have 0 and 2. You can have, do you have 1 and 2? You can have 1 and 2. And you can have a set itself, 0, 1, and 2. If we come up with all the possible combinations, so 1, 2, 3, 4, 5, 6, 7, and 8. So there are 8. So the formula is 2 to the power n for the number of subsets. Okay, so you can see in a case where you've got 2 to the power 2 is 4, we have got 3 to the power 3 is 8. That's how you find the number of subsets. So a subset is a set that is contained in another set. An empty set and the set itself are also subsets of a given set. Now, under subsets, we have what we call proper and improper subsets. So if I can take you back to an example where we have set A containing members 1 and 2. So let's just list down the subsets. We said an empty set 1, 2, and then 1 and 2. So these subsets that are less than the set itself, they are the ones that we call proper subsets. Proper. They are less than the set itself. Now, the subset which is a set itself, or in short, a subset which is equal to the set, is what we call an improper subset. Okay. So now the symbol for a proper subset is, you can say, if you're going to call this set C, you can say C is, okay, it's a bit confusing. Let me use a different letter. If you can say that is X, you can say X is a proper subset of A, in that all the elements of X are contained in A, but X is also less than what? X is also less than A. That's the interpretation of a proper subset. Now, on the other hand, for the improper subset, you can say we don't have any symbol for an improper subset for your own information. We don't have any symbol. So in such a case, we can just, there's nothing we can do but just say that X. We can just say, if we call it Y, you can just say Y is a subset of A. Now, notice that I can also say that X is a subset of A. It's only necessary if I didn't want to explicitly make a point to say it's a proper. That's when I leave out the dash. But in a general sense, you can say it's a subset by using this symbol. Okay. So this is what we call now proper and improper subsets. So if we are going to get back again, the formula for determining the number of subsets is 2 to the power n. The formula for determining the number of proper subsets is 2 to the power n minus 1. So that one we're removing is the set which is equal to itself. So for a case where we add 4 subsets, the number of proper subsets are 3. For a case where we add 8 subsets, the number of proper subsets were 7. Let me add a bit of some detail under subsets. So I've said, if you're going to have a case where, let me get you back to set A, and then set A is having members 1, 2, 3. If you're going to look at set B, having members 1 and 2. In this case, definitely, we can say B is a proper subset of A, because B has got 1 and 2 contained in set A, but A is bigger than B, right? Okay. Now, if I was going to say B is generally a subset of A, I wouldn't be wrong either. Okay. So the basic idea is the interpretation of this one is that it may either be equal or less than the other set. Okay, so if I'm going to have set C containing the same elements as A, the only way I can express it as a subset would be C is a subset of A. Okay, there's no other way. I can't use this. Okay, so I know some textbooks, some sites would tell you this symbol implies improper. That's not the case. It's just that there's no other way we can actually present it. But the basic idea is that when you see something like this, it denotes two possible cases. Either it may be a proper or an improper. In short, this symbol is a general symbol for a subset. Okay, so I needed to mention that if you're going to compare again set B and A, we can call A to be a superset since that is where B is contained. So A is a superset of set B. B is a subset of A. I thought that is also very important to basically get to mention. And then the other symbol that I wanted to mention is not subset. Okay, if you're trying to indicate that something is not a subset. So if you're going to talk about set X containing 0, 1, you see that 0 is not contained in A. So obviously you can say that X is not a subset of A. So I thought that symbol would also be very useful, very important. And of course, I think this would mean X is not a proper subset, but I think it would make more sense if you draw a dash to say X is not a subset explicitly in any form. Okay. So let's proceed now. Now a power set is very simple and straightforward. So I'll take you back to A. If you're going to say A is having 1, 2, let me add the new member 3. What are the subsets you have? The subsets of A, we have an empty set, we have a set containing 1, we have a set containing 2, we have a set containing 3. We can now have possible combinations 1 and 2, 2 and 3, and then you can have 1 and 3. You can have the set itself 1, 2, and 3. So if I'm going to group these in a set and then open a set and close a set and then add commas, so a power of a set is a set that includes the subset. So a power set is a set of subsets. So if I say the P of A, the power set of A, it is a set containing the subsets of set A. That is what a power set is. Very simple and straightforward. That's why I said it makes more sense by first of all reviewing what subsets are. Okay? So now that you've understood the basic introduction to our set theory, as we proceed and look at other concepts that are going to be easy, as we look at the laws under set theory, as we look at practice questions involving set builder notation, set interval notation, the Venn diagram, and then many more things. We'll proceed, look at, of course, the sides, binary operations, complex numbers after everything. Okay, thank you very much for watching the introduction. I hope you enjoy your journey as we proceed.